Hello everyone. Today we are doing a quick video on series, which is the second part of Unit 4. So we're going to take a look at series. This is a review, so we've already learned this material. Before I get started, some hand sanitizer, making sure that we are safe. And today we are learning about series. So to start off, series is looking at the sum of terms from a sequence. So series is a sum of terms, or sorry, term values from a sequence. And so we're taking those term values and we're adding them all up. And we can talk about taking all of the values, all of the term values, and adding all of them up. We can also look at just a few of the term values and add up a couple of them. For example, if we look at the sequence 1, 3, 5, 7, 9, and so on, here we could think about adding up some of the term values, for example, just the first 3 term values. So 1 plus 3 plus 5 to give us 9. And we have some notation to make it a little bit easier to talk about adding up just some of these term values. That notation is partial sum notation. So partial sums. So the nth partial sum is the sum of the first n terms. So the n number of terms. For example, here we have the third partial sum, and we use the notation s sub n. So s is the sum partial sum, and then n is the number of terms we're adding up. So here we have s sub 3 is the sum of the first 3 terms, which is 9. So here we talk about adding up the partial sums, or the sums of the first few terms from the sequence. We can also talk about sums using something called sigma notation. So really quickly, if you recall, sigma notation looks like, this. We have k equals some value. We have some number on top, and then we have some term number over here in terms of k. And k doesn't always start at 1. Sometimes it's 1, sometimes it could be 5. Here, for example, if we wanted to look at the sum of the first 3 terms, k starting at 1, going up to 3 of our sequence up here, then here our sequence equation, the term value equation, can be used. Our first value plus n minus 1, k minus 1 times d, 2. And what we do here is we go step by step. K equals 1, plug it in to get 1. K equals 2, we plug it in, we get 3. K equals 3, we plug it in, we get 5. And then we stop and we add up all of these term values. So we get 9. So this is another way of saying the nth partial sum if we go from k equals 1 to n. This is the third partial sum. Sigma notation is useful as opposed to partial sum notation because we can start at values other than 1. So we could start at k equals 2 and then go up to the 4th term value of that same sequence we have above. So here we're looking at k equals 2. So starting here, and we're going up to the 4th term value. So we're going to be adding up these 3 terms. So in this case, we have 3 plus 5 plus 7, which gives us 15. So this is equal to 15. So we're adding up some of the terms, not the first few terms, but we're starting at 2 and then adding up a few more terms. So this is how we look at sigma notation. We can describe series using 2 different labels. First, there are arithmetic series. arithmetic series are looking at the sum of term values from an arithmetic sequence. So we're adding up the term values from a sequence that is arithmetic. So an example of an arithmetic series is what we saw before. Here our sequence above was 1, 3, 5, 7, and so on. This is arithmetic because we're adding 2 to get from one term value to the next. And for our series, instead of having those commas, we just rewrite it as a summation. So 1 plus 3 plus 5 plus 7 plus, and so on. So this is what our arithmetic series would look like. Geometric series are similar to arithmetic series, except we're looking at a geometric sequence. One note is we're still looking at the sum of term values. So we're still adding all of our values together. The difference is that the values come from a sequence that is geometric. So term values from a geometric sequence. For example, a sequence we could look at is 2, 4, 8, 16, and so on. Here we have a geometric sequence because we are multiplying by 2 each time to find our next term value. Our series in this case would be all of those term values except adding them up. So we are still adding all of these term values together. But to find our next term value, we multiplied by that common ratio of 2. We have some equations to help us out with finding partial sums really quickly for arithmetic and geometric series, because it can be kind of annoying to have to write out and find every single term value and then add them all up. So first, looking at arithmetic partial sums. Again, partial sums are notated as S sub n. For arithmetic series, the nth partial sum can be found by taking n, dividing by 2, and multiplying it by t1 plus tn. We have another equation that we could use too if we have other information about our sequence. So maybe we don't know what t sub n is equal to. We could also use this equation n over 2 times 2 times t1 plus n minus 1 times d. So here we just replaced tn with n minus 1 times d. And we have another t1 in there. And that comes from our sequence equations. For geometric sequences, we can quickly find partial sums by using the equation S sub n equals t1 times 1 minus r to the n power over 1 minus r. So r is our common ratio, t1 is our first term value, and n is the nth partial sum that we're looking for. Finally, the last part of series that we looked at was convergence. And convergence only applies to geometric series. So a geometric series converges if the sum that we end up with, you can think of ending up with as we keep on adding all these term values, and eventually we end up with some sum that is a fixed number. So what this means is that what we're adding as we get to large term values gets very, very small and basically becomes 0. For example, if we look at the series 1 plus 1/2 plus 1/4, here we're dividing by 2 each time, plus 1/8. Eventually, when we get to very large values of n, for example, n equals 20, we're going to be adding on basically nothing to our sum. T sub 20, in this case, the 20th term value is 1 over about 1,050,000. So about, which is about 0.000001. So we're basically adding on nothing when we get to large n values. Formally, our book defines this as a series converges to S if the partial sums S sub n stay arbitrarily close to S as n gets very large. So eventually we're basically adding on nothing and we're staying at that sum S, that number S. And this happens because when we look at our term values, the term values here are getting smaller and smaller and smaller. And this is because we're multiplying by some value that is less than 1. So here, for example, we're multiplying by 1/2. So the term value becomes smaller and smaller. So we can determine if a series converges by looking at the common ratio. A series converges if and only if, which just means that the statement goes in both directions. The absolute value of the common ratio is less than 1. So that's how we can quickly determine if a series converges. The value that it converges to, S, is equal to T1 over 1 minus R. So just a shortened version of the partial sum equation that we had above. To solve word problems with series, we can go through a few steps. First, we want to identify if our problem is a arithmetic or geometric, and also identify if we're looking at a sequence, so a list of numbers, or a series, a summation of term values. Secondly, identify what information we know in the problem about the arithmetic or geometric sequence or series from number 1. And then thirdly, we can answer the questions usually by using our formulas or equations with our information from number 2. Okay, so a quick recap of what we talked about today. Today we were looking at series. We said series are sums of term values from a sequence. So we take these term values and we end up adding them up. A partial sum is just a sum of the first n terms. So the third partial sum is the sum of the first 3 terms here. Looking down, we started to talk about sigma notation. Sigma notation is looking at starting at the k equals 1 and then going to 2, 3, 4, going all the way up until we get to that top number n. And this is the value that we're adding on, 1, 3, 5, and so on. Sigma notation can start at a value other than 1, so we could start at the second term and go up to the 4th term. We talked about arithmetic series, which are sums of term values from an arithmetic sequence. Geometric series are sums still of term values from a geometric sequence, so multiplying rather than adding to get from one term value to the next. So we're still adding each time. We talked about arithmetic partial sums. We have 2 equations, as we can see here. For geometric partial sums, we have 1 equation here. Finally, we talked about convergence. Convergence means that the value that we're adding on, the term value, becomes very, very small as n gets very large. A series converges if and only if absolute value of r is equal to 1. So that's how we can determine convergence, and then we can find the value to which it converges using this equation down here. Lastly, with word problems, we want to identify what kind of sequence or series we're looking at, identify what information we know, and then finally use our formulas from our notes on this unit and on this video and the previous video to answer the questions.